There's a hidden conversation happening across the universe, one so vast and subtle that we've only just begun to eavesdrop. Picture this: two black holes, separated by millions of light years, locked in a silent dance, not through light or sound, but through invisible threads woven into the fabric of space-time itself. These cosmic titans, long thought to be solitary monsters lurking in the darkness, might actually be whispering secrets to one another, their gravitational ripples and quantum entanglements forming a web of connection we're only starting to understand. And what if I told you that unraveling these threads could rewrite our understanding of reality? For centuries, black holes have been the ultimate cosmic mysteries, places where gravity is so intense that not even light can escape. But what if their true nature isn't just about destruction? What if they're also cosmic architects, shaping the universe in ways we're only beginning to grasp? Recent breakthroughs in astrophysics have revealed something astonishing. Black holes might be linked across unimaginable distances, their fates intertwined by forces deeper than gravity alone. Imagine a universe where a black hole in one galaxy can somehow feel the presence of another, not through any known signal, but through something even stranger, like echoes in the quantum void or vibrations in the very structure of spacetime. This isn't just science fiction, it's the cutting edge of discovery, where theories about wormholes, entangled particles, and hidden dimensions collide with the raw power of observation. Scientists are now piecing together clues from gravitational wave detectors, space telescopes, and quantum experiments, all pointing to a reality far more interconnected than we ever dreamed. And here's the most thrilling part: by decoding these cosmic threads, we might finally answer some of the biggest questions in existence. How did the universe begin? What lies beyond the event horizon? And could these invisible connections be the key to unlocking the deepest secrets of time, space, and even the nature of reality itself? Strap in, because this journey will take us to the edge of what we know and beyond. To truly grasp how black holes might be connected across the void, we first need to understand the bizarre reality of what they actually are. Think of a black hole not just as a cosmic vacuum cleaner, but as a knot in the fabric of spacetime itself, a place where the rules of physics as we know them twist into something unrecognizable. When a massive star exhausts its fuel and collapses under its own weight, it doesn't just fade away. It leaves behind a gravitational fingerprint so intense that it punches a hole in reality, warping space and time into a one-way street where everything that crosses the event horizon vanishes from our observable universe. But here's where it gets even stranger. Black holes aren't just passive traps, they're dynamic, chaotic, and surprisingly messy eaters. As they devour nearby gas, dust, and even stars, they spew out jets of energy and radiation so powerful they can outshine entire galaxies. And their influence doesn't stop at the edge of their gravitational grip. Like stones dropped into a pond, their presence sends ripples through space-time gravitational waves that stretch and squeeze the cosmos itself. These waves, first detected in 2015, proved that black holes don't just sit silently in space. They move, collide, and send tremors across the universe, whispering their existence to anyone or anything listening. Now, imagine if those whispers aren't just random echoes. What if they're part of a conversation? Scientists are now uncovering clues that black holes might be linked through something far more profound than gravity alone. Quantum entanglement, a phenomenon where particles remain mysteriously connected across vast distances, could be playing a role. Picture two black holes, each with particles entangled at the quantum level, creating an invisible bridge between them. Even if they're on opposite sides of the universe, a change in one could instantly affect the other, defying our classical understanding of space and time. Add to that the mind-bending possibility of wormholes, theoretical tunnels through space-time that could connect black holes like secret passageways, and suddenly, the universe starts to look less like a collection of isolated objects and more like a vast, interconnected web. This isn't just speculation. Cutting-edge telescopes and detectors are now picking up patterns that hint at these hidden connections. From the way black holes spin in eerie synchronization to the unexplained correlations in their outbursts of energy, the evidence is stacking up. And if we're right, unraveling these cosmic threads could rewrite not just astrophysics, but our very understanding of reality itself. Because if black holes can talk to each other across the void, what else might be part of this universal conversation? Einstein's theory of general relativity gave us the first real glimpse into the nature of black holes, painting them as monstrous distortions in space-time where gravity reigns supreme. But even he might have been stunned to see how far we've pushed his ideas and how much stranger the universe has become. His equations showed us that massive objects like stars and black holes don't just sit in space, they bend it, twist it, and mold it like a sculptor shaping clay. Yet today, we're staring at phenomena that his framework alone can't fully explain. What happens when gravity meets the quantum world? Could the same equations that predicted black holes also hint at invisible highways linking them across the cosmos? Take quantum entanglement, for instance, a phenomenon so bizarre Einstein himself famously called it spooky action at a distance. Particles born together remain mysteriously connected, instantly influencing each other no matter how far apart they drift. Now imagine scaling that up to black holes. If two black holes share entangled particles, could a change in one trigger an instant response in the other, defying the speed of light? Some physicists think so, suggesting that these cosmic giants might be bound by quantum threads woven into the fabric of reality itself. And if that's true, it would mean black holes aren't just isolated pits of darkness, they're nodes in a vast, invisible network. Then there's the tantalizing idea of wormholes, theoretical shortcuts through spacetime that could connect distant black holes like cosmic subway tunnels. Einstein's equations actually allow for such structures, though they'd require exotic matter or energies we don't yet understand to stay open. Still, the possibility is irresistible. Picture two black holes, each the mouth of a wormhole, bridging galaxies in an instant. Matter falling into one could, in theory, emerge from the other, creating a hidden pipeline across the universe. It sounds like science fiction, but the math doesn't rule it out. And if wormholes exist, they'd be the ultimate cosmic connectors, turning black holes from lonely predators into gatekeepers of a far more interconnected cosmos. But the strangest twist might come from the holographic principle, a radical idea suggesting that our three-dimensional universe, black holes and all, could be a projection of information encoded on a distant two-dimensional surface. If that's the case, then black holes might not just be objects in space but holograms of deeper, more fundamental processes. Their interactions could be shadows of a hidden code governing reality itself. It's a concept that bends the mind, yet it's taken seriously by physicists exploring the edges of known science. So where does that leave us? Einstein's legacy gave us the tools to find black holes, but their secrets are leading us far beyond his vision. From entanglement to wormholes to holographic universes, every new discovery peels back another layer of mystery, revealing a cosmos more connected and more bewildering than we ever imagined. The question isn't just how black holes interact. It's whether unraveling their hidden conversations might rewrite the rules of physics altogether. The year 2015 marked a turning point in our cosmic eavesdropping the moment we first heard the universe whispering. When the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faint tremors of two black holes colliding over 1 billion light-years away, it wasn't just a scientific triumph. It was the crackling static of a cosmic radio finally tuning into a channel we never knew existed. Gravitational waves, ripples in the fabric of space-time itself, were no longer just equations on Einstein's chalkboard. They were real, detectable, and carrying messages from the darkest corners of the universe. Think of these waves like the vibrations of a colossal drumhead stretched across existence. When black holes spiral toward each other, their immense gravity churns space-time like a spoon stirring honey, sending out waves that travel at the speed of light. By the time they reach us, those ripples are weaker than the width of an atom, yet they carry the fingerprints of the most violent events, imaginable collisions that shake the cosmos. But here's what's truly astonishing. These waves might be more than just cosmic background noise. They could be a language, a way for black holes to transmit information across impossible distances. Imagine if each gravitational wave carried encoded details about the black holes that created it, their masses, their spins, even clues about what lies beyond their event horizons. Some theorists suggest these waves might function like interstellar telegrams, packed with data about the conditions that birthed them. It's as if every black hole collision leaves behind a cosmic voicemail, waiting for us to decipher it. And if that's true, then LIGO detections aren't just scientific milestones, they're the first pages of a universal dictionary we're only beginning to learn how to read. Yet gravitational waves might be just the opening act in this cosmic dialogue. While they prove black holes can influence each other through space-time, other forces could be at work too: quantum entanglement, threading black holes together like invisible puppet strings, or wormholes stitching distant corners of the universe into a single tangled web. The more we listen, the more the universe seems less like a collection of isolated objects and more like a living, breathing network, humming with conversations we're only starting to overhear. And if we can crack the code hidden in these waves, we might not just unlock the secrets of black holes, we might uncover the rules of a hidden cosmic internet, connecting everything from the tiniest particles to the largest structures in existence. So the next time you look up at the night sky, remember, it's not silent. It's alive with vibrations, whispers, and echoes, a symphony of gravitational waves carrying stories from the edges of reality. And we've only just begun to listen. Quantum entanglement might sound like the stuff of science fiction, but it's one of the most well-documented and bewildering phenomena in physics. Picture two particles born together, their fates intertwined in a way that defies common sense. Change the state of one, and its partner instantly responds, no matter if they're a millimeter or a galaxy apart. Einstein called it spooky action at a distance, and for decades it seemed like a quirky feature of the tiny quantum world. But what if this strange connection isn't confined to particles? What if entire black holes, cosmic leviathans with gravity so strong they warp reality, are entangled too? The implications are staggering. If black holes share entangled particles, they could communicate instantaneously, bypassing the universe's speed limit, the speed of light. Imagine two black holes, each holding a piece of the same entangled pair. A shift in one could trigger an immediate reaction in the other, as if they were two ends of a cosmic telephone line with zero delay. This isn't just theoretical. Recent simulations have shown that entangled black holes might naturally form wormholes, hypothetical tunnels through space-time that act like shortcuts across the universe. In this scenario, entanglement wouldn't just link black holes, it could physically bridge them, turning science fiction into scientific possibility. Think of it like a cosmic version of threading a needle through folded fabric. If spacetime is the fabric, entanglement might be the needle, stitching together distant points in ways we're only beginning to map. Some physicists argue that every pair of entangled black holes could be connected by a microscopic wormhole, a hidden tunnel lurking beneath the equations. It's a radical idea, but it hints at something even deeper. That entanglement and gravity, two pillars of modern physics, might be two sides of the same coin. The real mind bender: if black holes can share information instantaneously through entanglement, it challenges our most fundamental notions of cause and effect. In a classical universe, events unfold in orderly sequences. Cause comes before effect, and nothing travels faster than light. But entangled black holes could upend that logic, creating scenarios where an effect might precede its cause, or where distant objects act as if they're a single entity. It's as if the universe has been running on invisible rules we're only now deciphering. And here's where it gets even wilder. If entanglement does forge wormholes between black holes, it could mean these cosmic giants aren't just isolated traps for matter and light. They might be part of a vast, hidden network, a quantum internet woven into the fabric of spacetime itself. Every collision, every burst of energy from a black hole could ripple through this network, transmitting information in ways we're only starting to imagine. The universe, it seems, is far more interconnected than we ever dreamed, and black holes might be its most mysterious messengers. So the next time you hear about quantum entanglement, don't just think of tiny particles in a lab. Think of black holes, those titans of gravity whispering to each other across the void, bound by threads of quantum weirdness that defy space and time. And remember, the deeper we look, the stranger and more beautiful the cosmos becomes. Wormholes have danced through the imaginations of science fiction fans for decades. Those fantastical tunnels through space and time, offering instant shortcuts across the cosmos. But strip away the Hollywood gloss, and you'll find something even more astonishing. These cosmic passageways aren't just fantasy. They're rooted in real physics, emerging from the same equations that describe black holes and the fabric of spacetime. Imagine two black holes, each acting like a doorway, connected by a hidden corridor that bends the universe like a folded piece of paper. Step into one, and you could, in theory, emerge from the other, millions of light years away in the blink of an eye. It sounds impossible, yet the math doesn't just allow for it, it practically demands it. Einstein and his colleague Nathan Rosen first stumbled upon this idea in the 1930s while playing with the equations of general relativity. They realized that the extreme curvature of spacetime around a black hole might not end at a singularity, a point of infinite density, but could instead funnel into a bridge leading to another black hole elsewhere. These Einstein-Rosen bridges, as they were called, became the first crude blueprints for wormholes. But there was a catch. These theoretical tunnels were unstable, snapping shut faster than anything could pass through. To keep them open, you'd need something exotic like matter with negative energy, a substance that defies gravity by pushing space outward instead of pulling it inward. No one knew if such material existed, but the door to possibility had been cracked open. Fast forward to today, and the plot has thickened. Quantum physics suggests that entangled black holes, those mysteriously linked through spooky action at a distance, might be threaded by microscopic wormholes. Picture two black holes sharing a quantum connection, their entangled particles acting like invisible stitches sewing a tunnel through spacetime, the wildest part. This isn't just speculation. In 2013, physicists Juan Maldacena and Leonard Susskind proposed that entanglement and wormholes might be two sides of the same cosmic coin. Their ER equals EPR hypothesis suggests that when particles are entangled, a tiny wormhole lurks beneath the equations connecting them, Scale that up to black holes, and suddenly, those hypothetical tunnels become far more plausible. But let's be clear, no one's packing a suitcase for a wormhole vacation yet. Even if these passages exist, they'd likely be incredibly narrow, prone to collapsing, or require energies we can't yet harness. And then there's the paradox problem. If you could send information, or worse, yourself through a wormhole, you might violate causality, arriving before you left and rewriting history in ways that make physicists shudder. Yet these hurdles haven't stopped scientists from probing the possibilities. From lab experiments simulating wormhole dynamics to telescopes scanning for gravitational echoes that might hint at their existence, the hunt is on. Here's the real kicker. If wormholes do connect black holes, it would mean the universe isn't just vast, it's intimately interconnected, with hidden highways threading through the darkness. Black holes wouldn't be the end of things, they'd be waypoints in a sprawling cosmic subway system, shuttling matter, energy, or even information across unimaginable distances. And that changes everything. Suddenly, the universe feels smaller, stranger, and more alive with possibility. Whether wormholes remain theoretical curiosities or become the next great discovery, one thing's certain: the line between science fiction and science fact has never been thinner. The holographic principle turns our understanding of reality inside out, literally. Imagine the universe as a cosmic cinema screen, where every star, galaxy, and black hole we see is just a projection of information encoded on a distant, two-dimensional surface. It's as if the three-dimensional world we experience is an illusion, a hologram painted with data, and nowhere does this idea get stranger or more compelling than when applied to black holes. These gravitational behemoths, long thought to be cosmic dead ends where information vanishes forever, might actually be the universe's most sophisticated hard drives, storing every bit of data that falls into them, not in some hidden interior, but right on their surfaces, their event horizons. Think of a black hole's event horizon like the surface of a bubble, shimmering with unimaginable amounts of information. According to the holographic principle, every particle, every atom, every shred of light swallowed by the black hole leaves an imprint there, etched into space-time itself. It's as if the black hole doesn't destroy information but compresses it into a flawless, two-dimensional code. This idea solves one of physics' biggest headaches, the information paradox, which asks whether data truly disappears when it crosses a black hole's threshold. If the holographic principle holds, the answer is no. The information isn't lost, it's transformed, scrambled into a language we're still learning to read. But here's where it gets even wilder. If black holes store information holographically, they might not be isolated vaults. They could be nodes in a vast cosmic network, exchanging data through their entangled event horizons like servers in a celestial internet. Picture two black holes, each encoding information on their surfaces, but linked by quantum entanglement or even microscopic wormholes. A change in one could ripple through to the other, transmitting information across the universe instantaneously. No wires, no signals, just the hidden architecture of spacetime itself. This isn't just poetic speculation. The math behind the holographic principle has already reshaped how physicists think about gravity, quantum mechanics, and the fabric of reality. It suggests that the universe might fundamentally be a web of information, with black holes as its most intense processors. And if that's true, then every collision, every merger, every burst of Hawking radiation isn't just a physical event, it's a cosmic computation, a step in some grand calculation we're only beginning to glimpse. So what does this mean for us? If the holographic principle is right, reality might be far more interconnected and far more malleable than we ever imagined. Black holes wouldn't just be cosmic vacuums. They'd be libraries, routers, even artists painting the universe's story on the thinnest possible canvas. And as we learn to decode their holograms, we might not just solve the mysteries of black holes, we might crack the code of existence itself. Black hole binaries are the universe's most dramatic tango. Two cosmic monsters locked in a gravitational embrace, whirling around each other at speeds that bend the fabric of spacetime. Picture two dancers spinning faster and faster, their movements growing frantic until they finally collide in a crescendo of energy. But these aren't just any dancers. They're black holes, each with a gravitational grip so fierce that their final merger sends ripples across the cosmos, gravitational waves powerful enough to distort the very shape of space as they pass through Earth. Yet beneath this violent ballet lies something even more intriguing, hints that these binary pairs might be communicating in ways we don't fully understand. Take the case of one particularly strange binary system, where two black holes orbit each other in near-perfect synchrony, their spins aligned as if choreographed by some unseen hand. Statistically, this shouldn't happen by chance. Black holes born from separate stellar collapses should spin in random directions, like tops launched haphazardly across a table. But in these systems, they often move in eerie harmony, as if they've been whispering secrets to one another long before they were paired. Could there be some hidden mechanism, some cosmic thread linking them even before they became partners? Some scientists suspect these synchronized spins might be relics of their origins, forged in the turbulent hearts of dense star clusters where black holes frequently interact. Others propose something far more radical, that entangled quantum particles lingering from the black hole's fiery births could be subtly influencing their behavior across vast distances. Imagine two black holes, each harboring entangled remnants of their progenitor stars, their fates intertwined not just by gravity, but by the invisible bonds of quantum physics. Every twist, every rotation could be part of a dialogue written in the language of the subatomic world. Then there's the merger itself, a cataclysmic event that unleashes more energy than all the stars in the observable universe combined. As the black holes spiral inward, their gravitational waves crescendo into a cosmic chirp, a signal picked up by detectors like LIGO and Virgo. But buried in those waves could be clues about their deeper connection. The way they vibrate in the final moments, the echoes of their collision, these details might reveal whether they were always destined to meet, or if some deeper force nudged them together. And here's the tantalizing possibility. If black holes in binaries are truly linked by more than gravity, their mergers might not just be random encounters. They could be the universe's way of tying loose ends, of resolving hidden quantum entanglements, or even closing hidden wormholes. Every collision might be a cosmic handshake, a transaction in some vast, invisible network we're only beginning to map. So the next time you hear about black holes merging, remember, it's not just a spectacle. It could be a message, a clue, a piece of the puzzle in understanding how the universe stitches itself together. At the center of nearly every galaxy, lurking like a silent puppeteer, sits a supermassive black hole, an unfathomably dense titan with gravity so strong it can dictate the fate of billions of stars. These aren't just scaled-up versions of their stellar mass cousins. They're cosmic architects shaping the very galaxies they call home. Take Sagittarius, a star, the supermassive black hole at the heart of the Milky Way. With a mass 4 million times that of our Sun, it doesn't just sit there. It orchestrates the motion of stars around it, whipping them into frenzied orbits like a conductor guiding an interstellar symphony. But what if these giants aren't just local rulers? What if they're nodes in a vast, invisible network, woven together across the universe? Some astronomers now suspect that supermassive black holes might be connected through a cosmic web, a scaffolding of dark matter and gas that stretches across the cosmos, linking galaxies in a delicate lattice. Picture this web as the universe's nervous system, with supermassive black holes acting like relay stations, transmitting influence along its threads. When one black hole feeds, devouring gas in a violent outburst, could that energy ripple through the web, nudging distant black holes to awaken too? Observations of quasars' bright beacons powered by supermassive black holes show eerie patterns. Some flare up in sync across billions of light-years, as if responding to a signal we can't yet detect. The wildest possibility: these black holes might not just be linked by gravity or dark matter. Quantum entanglement, that same spooky connection binding particles, could scale up to cosmic proportions. Imagine two supermassive black holes, each harboring entangled particles from the early universe, their fates intertwined no matter how far apart they drift. A change in one could instantaneously affect the other, bypassing the speed of light entirely. It's a staggering thought that the universe's largest structures might be whispering to each other through quantum threads woven into space-time itself. And then there's their role in galaxy formation. Supermassive black holes don't just live in galaxies, they may have built them. In the early universe, their intense energy jets could have acted like cosmic blowtorches, heating surrounding gas and preventing runaway star formation. Without this balancing act, galaxies might have burned out too quickly, leaving no time for planets or life to emerge. In other words, these black holes aren't just destructive forces. They're cosmic regulators, fine-tuning the universe for complexity. So the next time you gaze at a galaxy, remember, its heart isn't just a dark abyss. It's a gravitational maestro, a potential quantum communicator, and maybe even a cosmic weaver tied to black holes in galaxies far beyond our own. The deeper we look, the more it seems the universe isn't just expanding, it's conversing, with supermassive black holes as its most enigmatic speakers. Dark matter is the universe's greatest ghost story, an invisible force that outweighs all visible matter 5-to-1, yet refuses to reveal itself except through its gravitational pull. We know it's there because galaxies spin faster than they should, their stars clinging to the edges as if held by unseen hands. But what if this elusive substance isn't just a cosmic glue? What if it's also the thread stitching black holes together across the void? Picture dark matter not as a featureless fog, but as a dynamic web, its particles clumping into dense streams and halos around galaxies and their central black holes. Some theories suggest these particles could behave in ways ordinary matter can't, forming long, filamentary structures that stretch between cosmic heavyweights like invisible puppet strings. Imagine two black holes, each shrouded in a halo of dark matter, linked by a river of these exotic particles. Though they never touch, never emit light, their dark matter bridges could transmit gravitational nudges or even quantum signals, turning isolated monsters into parts of a hidden network. The math gets even stranger when you consider certain hypothetical dark matter particles like ultralight actions, which behave more like waves than discrete bits of matter. These could form sprawling, coherent clouds around black holes, their wave-like properties allowing them to sync up across vast distances. If one black hole's action cloud vibrates, its counterpart light years away might resonate in response, creating a subtle but detectable cosmic telegraph. It's a tantalizing thought. Dark matter might not just fill the universe, it could be its silent communication grid. Then there's the wild card, primordial black holes. Some scientists speculate that dark matter itself might be made of ancient black holes, forged in the chaos of the Big Bang. If true, these stealthy relics could be everywhere, woven into the fabric of space-time, their gravitational whispers shaping the growth of galaxies and their supermassive siblings. In this scenario, dark matter isn't just connecting black holes, It might be them, a hidden population lurking in the shadows, quietly pulling the universe's strings. Of course, proving any of this is a monumental challenge. Dark matter famously refuses to interact with light or ordinary matter, making it nearly impossible to detect directly. But astronomers are getting creative. By studying the subtle warping of light around black holes' gravitational lensing, they might spot distortions that reveal the presence of dark matter threads. Others are hunting for oddities in black hole mergers, like unexpected delays in gravitational wave signals, which could hint at dark matter's invisible hand slowing things down. Whether dark matter is a cosmic switchboard or just a silent bystander, one thing's clear: the universe is far more than what we see. Every black hole might be a node in a vast, unseen network, whispering to its counterparts through channels we're only beginning to imagine. And if we ever crack the code of dark matter, we might not just solve a mystery, we could uncover the hidden architecture of reality itself. Imagine tossing a book into a roaring fire. The pages burn, the ink vanishes, but in principle, every word, every letter could be reconstructed from the smoke and ash if you had perfect knowledge of the physics involved. That's how our universe works. Information is never truly destroyed, just transformed. Now picture that same book falling into a black hole. According to Einstein's general relativity, the book, and every bit of information it contains, is irretrievably lost, crushed into a singularity where the laws of physics break down. But quantum mechanics insists that information can't just disappear. This clash between two foundational theories is the black hole information paradox, and it's been keeping physicists awake at night for decades. The stakes couldn't be higher. If information can vanish into a black hole, it undermines the bedrock of quantum theory, which governs everything from atoms to galaxies. But if it can't, then Einstein's description of black holes as simple, information-devouring pits is incomplete. Enter Stephen Hawking, who in the 1970s proposed that black holes aren't entirely black. They slowly leak energy, Hawking radiation, eventually evaporating into nothingness. But here's the catch: Hawking's calculations suggested this radiation was random, carrying no trace of the information swallowed by the black hole. Poof, information gone forever. The paradox was born. But what if the solution lies in the very connections we've been exploring? If black holes are entangled or linked by wormholes, could information escape through these hidden channels? Picture a black hole not as a cosmic trash compactor, but as a scrambler, shredding information into quantum code and imprinting it onto its event horizon like a hologram. As Hawking radiation escapes, it might carry away encrypted fragments of that code, which could later reconstruct the original information, just as smoke might theoretically reassemble into a book. This idea, known as the holographic principle, suggests black holes don't destroy information. They transform it into a form we're only beginning to decipher. Even wilder is the notion that entangled black holes could share information instantly across vast distances. If two black holes are quantumly linked, information falling into one might reappear in the other, like a letter passing through a cosmic trapdoor. It's a radical solution to the paradox, but it hints at something profound: that black holes might not be the end of information, but gateways to a deeper layer of reality where the rules are rewritten. The latest twist: some physicists argue that resolving the paradox might require merging quantum mechanics and gravity into a single theory, a theory of everything. If black holes are the universe's ultimate laboratories, where gravity and quantum effects collide, then cracking the information paradox could be the key to unlocking physics' final frontier. Every piece of data we recover from the edge of a black hole's abyss might be a clue to how the universe truly works, not as separate realms of the very large and the very small, but as a unified, interconnected whole. So the next time you hear about a black hole, remember, it's not just a cosmic mystery, it's a cipher waiting to reveal the deepest secrets of existence. Primordial black holes are cosmic wildcards, mysterious remnants that might have formed not from dying stars, but from the violent chaos of the Big Bang itself. Picture the universe in its first fraction of a second, a seething cauldron of energy and density so extreme that random fluctuations could have collapsed into knots of gravity powerful enough to birth black holes on the spot. Unlike their stellar-born cousins, these primordial relics could range from the size of an atom to the mass of 1,000 suns, scattered across the cosmos like invisible breadcrumbs from creation. And if they exist, they might be far more than ancient oddities. They could be the hidden architects of everything we see. One of the most tantalizing possibilities is that these primordial black holes are the elusive dark matter we've been searching for. Think about it. Dark matter doesn't emit light, doesn't interact with ordinary matter except through gravity, and yet it outweighs the visible universe 5 to 1. Primordial black holes fit that description perfectly. They'd be stealthy, drifting unseen through galaxies, their gravity tugging on stars and gas just as dark matter does. Some could be as light as asteroids, others as massive as supermassive black holes, all woven into the fabric of space since the dawn of time. But here's where it gets even stranger. If these ancient black holes formed in the early universe, they might have been born entangled, quantumly linked in ways that defy classical physics. Imagine two primordial black holes, created microseconds apart in the Big Bang's fury, forever bound by invisible threads. Even if they're now on opposite sides of the cosmos, a change in one could ripple through to the other instantaneously, as if the universe itself keeps them in sync. That kind of connection could explain why some black holes today seem to move in eerie harmony, their spins aligned across impossible distances. Then there's the question of scale. If primordial black holes come in all sizes, from microscopic to monstrous, they could be hiding in plain sight. The tiniest ones might evaporate in a flash of Hawking radiation, leaving behind faint bursts of energy we've yet to detect. The larger ones could lurk in the voids between galaxies, their gravity subtly bending light from distant stars, a phenomenon astronomers are already hunting for. And if they're clustered in halos around galaxies, they might be the invisible scaffolding that holds the cosmic web together. The implications are staggering. If primordial black holes are real, they'd rewrite not just the story of dark matter, but the entire history of the universe. They could have seeded the first galaxies, their gravity pulling gas and dust into the structures we see today. They might even explain some of the universe's most puzzling signals, like the unexpected heft of certain black holes detected by gravitational wave observatories. How did these black holes grow so big, so fast? Maybe they didn't, maybe they've been here all along, silent witnesses to the cosmos's evolution. Of course, proving any of this is a monumental challenge. Primordial black holes leave no light to trace, no heat to measure, but scientists are getting creative. Some are scouring old data from telescopes, looking for telltale flickers of stars momentarily brightening as a hidden black hole passes in front. Others are listening for the faint echoes of Hawking radiation, the last gasps of evaporating black holes so small they'd fit in your hand. And in labs around the world, researchers are simulating the conditions of the early universe, trying to recreate the birth of these cosmic phantoms. Whether primordial black holes are the missing piece of the dark matter puzzle or just another fascinating dead end, one thing's certain: they remind us how much of the universe remains hidden in plain sight. Cosmos might be threaded with invisible giants whispering secrets from the dawn of time, and we're only just beginning to listen. Black hole jets are the universe's ultimate particle cannons, twin beams of energy so intense they can pierce through galaxies, stretching millions of light years into the void. Picture a supermassive black hole, its gravity devouring everything nearby, yet somehow flinging out jets of plasma at nearly the speed of light. These aren't just random eruptions. They're precision-engineered cosmic accelerators, channeling energy with the force of 1 trillion nuclear explosions. But what if these jets are more than just spectacular displays? What if they're cosmic lifelines, threading the universe together in ways we're only beginning to understand? Take the black hole at the center of galaxy M87, for example. Its jet stretches 5,000 light-years, a searing beam of electrons and magnetic fields visible even from Earth. For decades, astronomers assumed these jets were one-way streets energy blasting outward into empty space. But recent observations hint at something stranger. Some jets appear to curve, twist, or even interact with invisible structures, as if they're brushing against something we can't see. Could these jets be tapping into hidden networks of dark matter, or even connecting with other black holes across the cosmos? The mechanics behind these jets are mind-bending. As a black hole feeds, it doesn't just swallow matter, it spins, dragging space-time around it like a whirlpool. This creates a powerful magnetic field, twisted into a tight coil that acts like a cosmic railgun. Particles get caught in this magnetic tornado, accelerated to near light speed and shot outward along the black hole's poles. The result is a jet so energetic it can outshine entire galaxies. But here's the kicker: the same forces that create these jets might also link black holes together. If two black holes are aligned just right, their jets could theoretically interact, exchanging energy or even information across vast distances. Then there's the dark matter angle. Some theorists propose that these jets might plow through halos of dark matter, stirring up waves or triggering reactions we've yet to detect. Imagine a jet slicing through a river of invisible particles, leaving behind ripples that could, in theory, carry signals to other black holes. It's a long shot, but if dark matter interacts with black hole jets even weakly, it could mean these beams are part of a hidden communication network, a cosmic version of tapping messages through a wire. The most tantalizing clue: some supermassive black holes flare in sync across billions of light years, their jets firing up in eerie unison. Coincidence? Maybe, or it could be evidence of a deeper connection, a hidden hand orchestrating these eruptions through some mechanism we've yet to uncover. Whether it's entangled particles, dark matter filaments, or something even stranger, one thing's clear: black hole jets aren't just cosmic fireworks. They might be the universe's way of stitching itself together, one particle beam at a time. What if our universe isn't the only one? What if black holes, those cosmic vacuum cleaners we've been studying, are actually secret doorways to other realities? The multiverse hypothesis, once relegated to the fringes of science fiction, is now gaining traction among physicists, and black holes might hold the key to unlocking it. Imagine a black hole not as a dead end, but as a tunnel, a wormhole, stitching our universe to another, like a hidden passage between two rooms in an infinite cosmic mansion. The math behind this idea isn't just wild speculation. Some solutions to Einstein's equations suggest that the crushing singularity at a black hole's core might not be a terminal point, but a bridge to somewhere else entirely. Take the concept of entangled black holes, for instance. If two black holes are quantumly linked, their connection might not stop at our universe. Some theorists propose that their entangled states could span multiple realities, creating a network of wormholes threading through the multiverse. Picture this: a particle falling into a black hole in our universe could, in theory, emerge from its entangled partner in another universe, a cosmic game of telephone where the message skips across dimensions. It's a dizzying thought, but it's rooted in real physics. The same quantum weirdness that allows particles to communicate instantaneously across vast distances might also enable black holes to whisper to their counterparts in parallel worlds. Then there's the holographic principle, which suggests our three-dimensional universe could be a projection of information encoded on a two-dimensional surface at its boundary. If that's true, black holes might not just be objects within space, they could be glitches in the cosmic code, points where the projection frays and reveals the scaffolding of deeper dimensions. In this view, a black hole's event horizon might be less like a one-way trapdoor and more like a screen flickering between channels, each tuned to a different universe. Of course, this is all theoretical. No one's found direct evidence of other universes, let alone black holes acting as portals. But consider the strange behavior of certain black holes, like those that seem to remember their past interactions or exhibit quantum properties that defy classical physics. Could these anomalies be hints of something bigger, a multiverse tugging at the edges of our reality? The implications are staggering. If black holes truly connect universes, they'd rewrite not just cosmology but the very meaning of existence. Suddenly, the cosmos isn't a solitary bubble but part of an unimaginably vast tapestry, with black holes as the threads weaving it together. Whether this idea holds up or collapses under scrutiny, one thing's certain: the deeper we probe these cosmic enigmas, the stranger and more wondrous the universe becomes. Time near a black hole doesn't just slow down, it warps into something unrecognizable. Picture an astronaut orbiting just outside the event horizon, their watch ticking at a snail's pace compared to clocks back on Earth. This is Einstein's time dilation in action, gravity so strong it stretches seconds into years. But what if this extreme time warp isn't just an isolated quirk? What if it's the hidden mechanism synchronizing black holes across the cosmos? Recent observations have revealed something uncanny. Supermassive black holes in distant galaxies sometimes flare in unison, their bursts of energy echoing each other across billions of light years. Statistically, these coordinated eruptions shouldn't happen by chance, yet they do, as if some invisible metronome is keeping cosmic time. Here's where time dilation gets interesting. If two black holes are connected, whether by quantum entanglement, wormholes, or some deeper cosmic thread, their gravitational time warps could create a feedback loop. A flicker of activity near one black hole, slowed to a crawl by its extreme gravity, might reach its linked counterpart at just the right moment to trigger a mirrored response. It's like two pendulums swinging in perfect sync, not because they're touching, but because their rhythms have subtly aligned. The math behind this is as elegant as it is mind-bending. In general relativity, time isn't absolute, it's fluid, shaped by gravity and motion. For entangled black holes, this could mean their internal clocks tick at different rates relative to each other, yet remain perfectly coordinated through their connection. Imagine two musicians playing a duet, one on a mountaintop where time flows faster, the other in a valley where it drags. Despite the mismatch, their shared sheet music, the quantum link between them, keeps their notes harmonized. Similarly, black holes might use time dilation not as a barrier, but as a conductor's baton, orchestrating their behaviors across the void. Even stranger is the possibility that these time-synced black holes could be encoding information in their delays. Just as Morse code uses pauses between signals, the lag between a black hole's activity and its counterpart's response might carry hidden meaning. Astronomers have already noticed odd gaps in gravitational wave dated tiny hiccups in the expected rhythm of black hole mergers. Could these be cosmic semaphore messages threaded through the fabric of spacetime itself, Of course, proving any of this is a monumental challenge. Time dilation near black holes is so extreme that observing its effects directly is like trying to watch a tree grow in slow motion from another galaxy. But new telescopes and advanced simulations are offering glimpses. Some models suggest that if black holes share entangled particles, their time warps could create resonant frequencies, like tuning forks vibrating in harmony across the universe. Others propose that wormholes, if they exist, might naturally synchronize connected black holes by balancing their gravitational ticks like gears in a cosmic clock. The implications ripple far beyond astrophysics. If time itself can be harnessed as a cosmic synchronizer, it hints at a universe far more interconnected than we ever imagined. Black holes wouldn't just be isolated pits of gravity. They'd be timekeepers, their rhythms woven into the universe's hidden fabric. And every flicker, every flare, every gravitational wave might be part of a grander dialogue, one where time isn't a straight line but a symphony, conducted by the invisible hand of relativity. Dark energy is the universe's most enigmatic puppeteer, an invisible force not just stretching the cosmos, but actively rewriting its future. Unlike gravity, which pulls matter together, dark energy pushes space itself apart, accelerating the expansion of the universe at an ever-increasing rate. But what if this cosmic repulsion isn't just shaping galaxies and voids? What if it's also tugging at the invisible threads connecting black holes across the void? Picture spacetime as a vast, elastic fabric. Dark energy isn't merely stretching it, it's altering its very texture, thinning it out like dough rolled too thin. For black holes linked by quantum entanglement or hypothetical wormholes, this expansion could be pulling at their connections, stretching the bonds between them to their limits. Imagine two black holes tied by an invisible thread, drifting farther apart as the universe accelerates. Dark energy might not snap that thread outright, but it could be weakening it, like a rubber band slowly losing its elasticity over billions of years. Yet here's the twist: dark energy's influence might not be purely destructive. Some theories suggest that as spacetime stretches, it could also create new opportunities for connections to form. Think of it like a cosmic game of telephone wires. As old threads grow taut and fade, the expansion itself might weave new ones, knitting black holes into fresh networks we can't yet see. In this scenario, dark energy isn't just a force of separation. It's a dynamic participant in the universe's hidden dialogue, constantly reshaping the channels through which black holes communicate. The stakes couldn't be higher. If dark energy is actively reconfiguring these cosmic links, it could determine the ultimate fate of black hole networks, and by extension, the structure of the universe itself. Will the accelerating expansion eventually isolate every black hole, leaving them as silent, disconnected monoliths adrift in the void? Or could some deeper mechanism, like quantum entanglement's defiance of distance, keep them whispering to one another no matter how far apart they're pushed? Astronomers are already hunting for clues. By mapping the distribution of supermassive black holes across cosmic time, they've noticed something peculiar. The farther back they look, the more tightly clustered these giants appear. It's as if dark energy's grip has been steadily pulling them apart, unraveling an ancient web. But there are outliers, black holes that seem to move in sync despite the expansion, as if their connection transcends the stretching of space. Could these be the holdouts of a fading network, or evidence of something even stranger? One provocative idea is that dark energy itself might not be uniform. If it fluctuates in strength or density across the cosmos, it could create pockets where black hole connections remain strong, like islands of stability in an accelerating sea. In these regions, entangled pairs or wormholes might persist long after their counterparts elsewhere have been severed, forming hidden corridors in an otherwise dispersing universe. The implications ripple far beyond astrophysics. If dark energy influences black hole connections, it could mean the universe's fate isn't just expansion. It's a transformation of how matter, energy, and information interact on the grandest scales. Black holes might be more than just relics of dead stars or galactic anchors. They could be barometers of cosmic change, their hidden networks reflecting the push and pull between gravity's embrace and dark energy's relentless drive. So the next time you hear about the universe's accelerating expansion, remember, it's not just carrying galaxies away from each other. It might be quietly reweaving the fabric of reality itself, one black hole thread at a time. Black holes might appear as the ultimate cosmic vacuum, silent, dark, and seemingly simple. But beneath their monstrous exteriors lies a hidden layer of complexity, one that defies our everyday intuition: entropy. In physics, entropy measures disorder, the natural tendency of systems to descend into chaos. A spilled glass of water, a shuffled deck of cards, these are small examples of entropy at work. Yet black holes take this concept to staggering extremes. Their entropy isn't just high, it's unimaginably vast, dwarfing even the most chaotic systems we know. How can something that seems so featureless, a black hole's event horizon appearing smooth and blank, contain such unfathomable disorder? The answer lies in the quantum realm, where every bit of information swallowed by a black hole leaves an indelible mark. Consider this: when a star, a planet, or even an entire galaxy falls into a black hole, its intricate structure, every atom, every particle, every ounce of its history, is seemingly obliterated. But quantum mechanics insists that information can't truly vanish. Instead, it's scrambled, encoded into the black hole's event horizon like data, etched onto a celestial hard drive. The more a black hole consumes, the more disorder, the more entropy it harbors. This idea, first proposed by physicist Jacob Bekenstein and later refined by Stephen Hawking, revolutionized how we think about black holes. They aren't just gravitational tombs, they're the universe's most efficient archivists, compressing chaos into an invisible quantum ledger. Now, imagine two black holes entangled across the cosmos. If entropy is fundamentally tied to information, could these linked giants share their chaotic states? Picture a pair of dice tumbling in perfect sync, no matter how far apart they're thrown. In the quantum world, entangled particles behave this way. Their properties remain mysteriously coordinated. Scale that up to black holes, and you're left with a breathtaking possibility. Their entropies might be intertwined, their chaotic dances mirroring one another instantaneously, as if space-time itself is keeping score. This isn't just theoretical poetry. Some models suggest that entangled black holes could exhibit correlated entropy fluctuations, meaning a change in one's disorder would ripple through to the other, no matter the distance. It's as if the universe has a hidden accounting system, balancing chaos and order on a cosmic scale. And if that's true, it could explain why certain black holes, even those separated by billions of light years, seem to exhibit eerily similar behaviors, as if governed by the same unseen hand. The implications stretch far beyond black holes. If entropy can be shared across entangled systems, it might hint at a deeper truth, that the universe maintains equilibrium not through local interactions, but through vast, invisible networks. Black holes could be the ultimate test case, their entangled entropy revealing how chaos and order are woven into the fabric of reality itself. So the next time you think of entropy as mere disorder, remember, in the depths of a black hole, it might just be the universe's way of whispering secrets across the void. Quantum gravity is the holy grail of modern physics, the missing link that could finally explain how black holes communicate across the vast cosmic web. Right now, we're stuck with two rulebooks for the universe: Einstein's general relativity, which paints gravity as the curvature of spacetime, and quantum mechanics, which governs the bizarre behavior of particles at the smallest scales. Both work flawlessly in their own domains, but when they collide, like in the heart of a black hole, the equations explode into nonsense. That's where quantum gravity steps in, or at least where it should. Without it, we're like detectives trying to solve a cosmic crime with half the evidence, staring at black holes and wondering how their hidden conversations defy the laws we know. Take string theory, one of the leading contenders in this grand unification quest. It reimagines particles not as tiny dots, but as vibrating strings, each oscillation producing a different particle like notes on a cosmic guitar. In this framework, black holes might not be singularities at all, but tangled knots of these strings, their vibrations encoding information in ways we're only beginning to decode. Picture two black holes as instruments in an orchestra, their strings resonating in harmony across the void. A pluck on one could send vibrations through the fabric of spacetime itself, transmitting signals in a language we've yet to translate. String theory even suggests extra dimensions, hidden folds in reality where black holes might be threading connections we can't see, like roots intertwining beneath the surface of a forest. Then there's loop quantum gravity, a radically different approach that chops spacetime into tiny, indivisible chunks. Think of it as the universe's pixelated blueprint. In this model, black holes aren't bottomless pits but dense networks of these spacetime loops, their structure preserving information like a cosmic hard drive. Here's where it gets wild. If two black holes share entangled loops, their quantum states could remain linked no matter how far apart they drift. It's as if the universe stitched them together at the smallest possible scale, creating a hidden highway for information to travel. Loop quantum gravity also offers a stunning resolution to the singularity problem, the idea that black holes crush matter into an infinitely dense point. Instead, the loops might reach a maximum density, then bounce back, meaning a black hole's core could be a gateway to another universe or a reborn region of spacetime. But why does this matter for black hole connections? Because without quantum gravity, we're left guessing how entanglement, wormholes, or holographic principles could operate in the extreme gravity of these cosmic monsters. General relativity says spacetime is smooth and continuous. Quantum mechanics says it's grainy and probabilistic. Black holes exist where these descriptions clash most violently, and until we reconcile them, their whispers will remain muffled. Some theories even propose that quantum gravity might reveal black holes as cosmic transformers, turning gravitational energy into quantum signals, or vice versa, like a universal translator for the laws of physics. The race to crack quantum gravity isn't just academic. Every glimmer of progress, from lab experiments simulating black hole conditions to telescopes hunting for quantum signatures in gravitational waves, brings us closer to understanding how the universe stitches itself together. Whether through vibrating strings, woven loops, or some yet undiscovered framework, the answer will rewrite not just astrophysics, but our very notion of reality. Until then, black holes will keep their secrets, their connections hovering just beyond the edge of our understanding, waiting for the day we finally speak their language. Supercomputers are now unlocking secrets about black holes that telescopes alone could never reveal, by simulating entire cosmic networks inside their digital minds. Picture scientists feeding Einstein's equations into machines capable of crunching numbers at speeds unimaginable just decades ago, reconstructing the gravitational dance of black holes with startling precision. What they're finding defies expectations. These cosmic titans don't just drift alone in the void. Under the right conditions, they might arrange themselves into stable, intricate structures like atoms bonding into molecules or neurons firing in a vast cosmic brain. Take one groundbreaking simulation where researchers modeled thousands of black holes interacting in a virtual galaxy. Instead of chaotic collisions, something extraordinary emerged. The black holes began to synchronize, their orbits stabilizing into patterns that persisted for eons of simulated time, some paired up, circling each other in tight, rhythmic loops. Others fell into larger formations, their gravitational pulls balancing like celestial mobiles. The most striking result: these virtual black holes didn't just coexist, they organized as if following an invisible blueprint. It's as if the universe has a hidden preference for connection, weaving black holes into networks far more complex than we ever imagined. But how could such structures exist without tearing themselves apart? The answer lies in the delicate balance between gravity and motion. Just as planets orbit stars without crashing in, black holes in these simulations find equilibrium, their immense pulls offset by precise speeds and trajectories. Some models even suggest that dark matter, the universe's invisible scaffolding, could act like cosmic glue, its gravitational influence helping to stabilize these black hole arrangements across cosmic time. The implications are staggering. If black holes can form stable networks, the universe might be filled with invisible architectures, lattices of gravitational giants shaping the flow of galaxies, energy, and even time itself. Imagine a supermassive black hole at the heart of one galaxy, subtly tugging on another millions of light years away, not randomly, but as part of a vast, coordinated system. Astronomers have already spotted hints of this, galaxies clustering in unexplained alignments, their central black holes spinning in eerie synchrony. Could these be the fingerprints of a deeper cosmic order? Here's where it gets even wilder. Some theorists propose that black hole networks could function like quantum circuits, with entangled event horizons processing information on a scale that dwarfs human comprehension. In this view, the universe itself might be a kind of quantum computer, with black holes as its processing nodes, exchanging data through gravitational waves or hidden wormholes. It's a vision that blurs the line between astrophysics and information theory, suggesting that the cosmos doesn't just contain complexity, it is complexity operating at a level we're only beginning to decode. Of course, simulations aren't reality, but they're a crucial bridge between theory and observation, offering testable predictions. If future telescopes detect more black holes moving in unnatural harmony, or if gravitational wave observatories pick up unexpected echoes in their mergers, it could mean these digital experiments are onto something profound. Whether these networks are fleeting or fundamental, one thing's clear: the universe is far more than a collection of isolated objects. It might be a living, breathing web, and black holes could be its master weavers. Black hole echoes might be the universe's way of sending us a message in code, a faint, repeating whisper hidden in the static of gravitational waves. When LIGO first detected the ripples from colliding black holes, scientists expected clean, predictable signals, a rising chirp as the holes spiraled inward, then silence as they merged into one. But some researchers noticed something odd. After the main event, buried in the data were faint, repeating pulses like echoes bouncing off unseen walls. If these echoes are real, they could shatter our understanding of black holes, suggesting there's more beyond the event horizon than just empty, crushing darkness. What could produce these echoes? One tantalizing possibility is that black holes aren't the bottomless pits we thought. Instead, their event horizons might hide structures, exotic matter, quantum fuzz, or even the throats of wormholes acting like cosmic mirrors that reflect gravitational waves back into the universe. Picture shouting into a cave and hearing your voice bounce off distant walls. Now imagine the cave is a black hole, and the echoes are space-time itself ringing like a bell. Some theories propose that wormholes, those hypothetical tunnels through space-time, could leave exactly this kind of fingerprint. If a black hole's event horizon conceals a wormhole mouth, gravitational waves might ricochet inside its throat before escaping, creating delayed, repeating signals in the data. Not everyone's convinced, though. Skeptics argue these echoes could just be noise glitches in the detectors or artifacts of data processing. After all, gravitational wave astronomy is still in its infancy, and teasing faint signals from cosmic background static is like listening for a whisper in a hurricane. But the debate is far from settled. New studies using machine learning to sift through LIGO data have found more of these echo candidates, and upcoming observatories like the space-based LISA could settle the argument once and for all. If the echoes are real, the implications are staggering. Wormholes aren't the only possibility. Quantum gravity models suggest the event horizon might be a seething quantum firewall, a turbulent zone where space-time itself fractures into microscopic loops or strings. Gravitational waves hitting this chaotic surface could scatter like light through frosted glass, producing echoes without the need for wormholes at all. Then there's the holographic principle, which imagines the event horizon as a two-dimensional screen, encoding all the information that falls into the black hole. In this view, echoes might be the hologram's way of vibrating, its pixels shimmering like a disturbed pond. The most mind-bending idea, these echoes could be evidence of hidden cosmic threads, not just connecting black holes, but stitching the universe together at a fundamental level. If space-time has a granular structure like a fabric woven from quantum threads, black holes might be knots where those threads tangle and loop. Gravitational waves passing through these knots could resonate in ways that leave echoes, revealing the hidden architecture of reality itself. Whether echoes prove to be cosmic mirages or revolutionary discoveries, one thing's clear: black holes are still hiding secrets. Every flicker in the data, every anomaly in the signals, is a clue waiting to be deciphered. And if we're right, if these echoes are real, they could be the first hints of a universe far stranger and far more connected than we ever dared to imagine. The Fermi paradox has haunted scientists for decades. If the universe is teeming with potential life, why does it feel so eerily empty? One radical answer might be hiding in the darkest corners of space: black holes. Imagine an advanced civilization millions of years ahead of us, facing the same cosmic hurdles we do: the vast distances between stars, the limitations of light-speed travel. Instead of struggling against these barriers, what if they've turned to the universe's natural infrastructure? Black holes, with their extreme gravity and potential for entanglement, could be the galactic equivalent of subway stations, wormholes serving as tunnels between distant points. Think about how humanity has always harnessed natural phenomena. Rivers became highways, wind-powered ships, and now we're tapping into quantum mechanics for computing. An alien society might see black holes not as cosmic dead ends, but as tools. If entanglement links black holes across the universe, a signal or even matter sent into one could emerge from another instantaneously, bypassing the need for slow, energy-guzzling starships. It's like finding a hidden backdoor in the universe's code, but here's where it gets even stranger. If black holes are being used as communication hubs, their very nature would make them perfect for secrecy. Anything crossing an event horizon vanishes from our observable universe, making it impossible to detect from the outside. Advanced civilizations could be exchanging vast amounts of information through these cosmic portals, their messages hidden in gravitational wave patterns or quantum fluctuations, completely invisible to our current technology. And then there's the energy factor. Black holes aren't just gravity wells, they're power plants. The accretion disks around them emit unimaginable energy, and Hawking radiation, though faint, could theoretically be harvested. A civilization capable of tapping into that might not need stars anymore. They could thrive near black holes, drawing energy from them while using their connected networks to explore or even manipulate the cosmos. The unsettling implication: if this theory holds, the reason we haven't found aliens isn't because they're not out there. It's because they've moved beyond the need for radio signals or Dyson spheres. They're operating on a level we can't yet perceive, using the fabric of spacetime itself as their medium. We might be like ants on a forest floor, unaware of the highway being built above us. Of course, this is all speculative, but with every new discovery about black hole connections, from gravitational waves to quantum entanglement, the idea shifts from pure fantasy to a tantalizing possibility. Maybe the universe isn't silent. Maybe we're just listening for the wrong signals, while the real conversation is happening in a language written in gravity and quantum threads. The answer to the Fermi paradox might not be in the stars, but in the darkness between them. Black hole mergers are the universe's most violent symphonies, collisions so powerful they briefly outshine every star in the observable universe combined. When two of these cosmic titans spiral toward each other, their gravitational dance warps spacetime like a drumhead stretched to its limit, sending shockwaves across the cosmos at the speed of light. But beneath the chaos lies an eerie order, a pattern so precise that scientists can predict the exact frequency of the resulting gravitational waves before they even reach our detectors. It's as if the universe has composed a score for these events, with black holes as its reluctant musicians. What's truly fascinating, though, isn't just the energy released, it's what these mergers leave behind. Every collision doesn't just create a bigger black hole, it might also rewire the hidden architecture of the cosmos. Picture two black holes entangled in a quantum embrace long before they merge. As they collide, their event horizons stretch, merge, and finally settle into a new, unified surface. But does that connection sever, or does it transform? Some theories suggest the merger could amplify their entanglement, weaving a fresh thread into the cosmic web. It's like cutting two knotted ropes and fusing their ends. The original tangle might be gone, but the new bond could be even stronger. Then there's the space-time fabric itself. A black hole merger isn't just a local event, it's a seismic shift in the structure of reality. The gravitational waves ripple outward, but they also leave behind subtle distortions in their wake, like wrinkles in a blanket that never fully smooth out. These lingering warps could act as conduits, pathways where future black holes might find it easier to link up, almost as if the universe remembers where mergers have happened before. Astronomers have even noticed something peculiar. In dense galactic regions, black holes seem to merge more frequently than random chance would allow. Could earlier collisions be paving the way for new ones, like cosmic breadcrumbs guiding the next pair together? The aftermath of a merger also holds clues about the universe's hidden wiring. When two black holes become one, the new black hole rings down, vibrating like a struck bell as it settles into its final form. The tone of this ring, the specific frequencies of its gravitational echoes, can reveal whether the merged black hole is smooth, as Einstein predicted, or frothing with quantum structure. If the echoes deviate from expectations, it might mean the event horizon isn't the featureless surface we thought. Tiny quantum wormholes, holographic imprints, or even remnants of the original black hole's entanglement could be hiding just beneath the surface, subtly altering the ring's pitch. But here's the most tantalizing possibility. If black holes are indeed nodes in a cosmic network, their mergers might not just be in points, they could be rebirths. Imagine two entangled black holes colliding, their connections seemingly severed, only for the new black hole to inherit their combined quantum links. It could emerge as a supercharged hub tied to more distant black holes than either of its predecessors. In this way, the universe's web of connections wouldn't just persist through mergers, it would evolve, growing more complex with each collision. So the next time LIGO detects a gravitational wave chirp, remember, it's not just the death cry of two black holes. It could be the universe knitting itself together anew, one cataclysmic stitch at a time. There's a strange quirk at the heart of quantum mechanics, one that challenges everything we think we know about reality. Simply observing a particle can change its behavior, as if the universe is shy about revealing its secrets. This is the observer effect, and it's not just a quirk of tiny atoms in a lab. What if the same rule applies to the most massive objects in existence? What if our very act of studying black hole connections is altering them in ways we can't yet detect? Consider the double-slit experiment, where particles act differently when watched versus when left unobserved. Electrons fired through two slits create an interference pattern, a wave-like behavior, until you place a detector to see which slit they pass through. Suddenly, they act like particles, the pattern vanishes, and reality seems to reshape itself based on your curiosity. Now scale that up to black holes. Every time we point a telescope at a distant quasar or analyze gravitational waves from a merger, are we inadvertently nudging the system? Could the universe's most enigmatic objects be just as sensitive to observation as the tiniest quantum particles? The implications are dizzying. If black holes are entangled across vast distances or connected by wormholes, our attempts to measure one might send ripples through the entire network. Imagine dipping a net into a pond to study the fish, only to realize your net is tangling the very connections you're trying to map. Some theories suggest that black holes might encode information holographically, with their event horizons acting like quantum hard drives. If so, probing them could be like running a diagnostic on a cosmic computer, one that reboots or reconfigures itself in response to your queries. This isn't just philosophical musing. Recent work in quantum gravity hints that spacetime itself might be granular at the smallest scales, built from discrete pixels of reality. In such a universe, observation isn't a passive act, it's an interaction, a transfer of energy that could subtly tweak the system. Black holes, as the densest concentrations of spacetime curvature, might be especially sensitive to these tweaks. Every gravitational wave we detect, every photon we capture from an accretion disk, might leave an imprint on the black hole's behavior, like a detective's fingerprint on a crime scene. The most unsettling possibility: if black holes are nodes in a cosmic network, our observations could be reshaping the web itself. Just as social media algorithms adapt to your clicks, the universe might be learning from our experiments, adjusting its hidden connections in ways we can't predict. It's a cosmic version of the Heisenberg uncertainty principle. The more precisely we try to measure black hole connections, the more we might disturb them. Yet there's hope in the chaos. If our observations do influence black holes, the changes themselves could carry clues. Tiny anomalies in gravitational wave data, unexpected flickers in quasar light. These might be the universe's way of talking back, revealing the rules of engagement between observer and observed. We're not just passive witnesses to the cosmos, we're participants tangled in the same quantum web as the black holes we study. And that means every experiment, every observation isn't just uncovering reality, it's helping to shape it. Stephen Hawking's greatest insight wasn't about black holes' darkness, it was about their glow. In the 1970s, he stunned the physics world by proving these gravitational monsters aren't completely black. They radiate, not with light, but with a faint quantum whisper called Hawking radiation, particles born from the violent tug of war at the event horizon where gravity battles quantum mechanics. This glow is so feeble it would take a black hole with the mass of our sun longer than the current age of the universe to evaporate. But here's the revolutionary twist. This radiation might not just be random thermal noise. It could be a cosmic Morse code carrying encrypted messages about everything the black hole has ever consumed. And if black holes are entangled, those messages might not be destined for oblivion. They could be broadcasting to partners across the void. Picture a black hole as a cosmic librarian. Every book, every star, planet, or spaceship that falls in gets shredded at the atomic level. Classical physics says that information is gone forever, burned in the furnace of the singularity. But quantum mechanics insists the universe keeps perfect records. Hawking radiation could be how those records get preserved, not destroyed. As particles escape the black hole's grip, they might carry imprints of what fell in, like smoke preserving the shape of the fire that created it. Now imagine two black holes quantumly entangled, their fates intertwined. If one emits Hawking radiation laced with information, could its entangled partner somehow receive or reconstruct that data? It's as if the universe installed a backup system for reality itself, with black holes as its servers. This idea could crack open the black hole information paradox. The glaring contradiction between general relativity's claim that information vanishes in black holes and quantum theory's insistence it can't. If Hawking radiation encodes data and entangled black holes share it, then information isn't lost. It's just transformed, transmitted through channels we're only beginning to map. Some theories suggest these channels might resemble quantum teleportation, where information jumps between linked particles without traveling the space between them. Scale that up to black holes, and you've got a cosmic internet where data bypasses spacetime entirely. The math gets even wilder when you consider wormholes. Certain solutions to Einstein's equations show that entangled black holes could be connected by microscopic tunnels through spacetime. As one black hole emits Hawking radiation, those particles might traverse the wormhole, emerging near its entangled partner. From our outside perspective, this would look like information miraculously reappearing, as if the black holes were playing an interstellar game of catch with the universe's deepest secrets. But how could we ever test this? The signals would be unimaginably faint, buried in quantum noise over cosmic timescales. Yet physicists are getting creative. Some are developing quantum analogs of black holes in labs, using ultra-cold atoms or light pulses to simulate event horizons and Hawking radiation. Others are scouring gravitational wave data for anomalies, subtle hiccups in the expected signals that might hint at information transfer during black hole mergers. And then there's the holographic principle, which suggests all the information inside a black hole is smeared across its two-dimensional surface like a cosmic QR code. If that's true, Hawking radiation might be the universe's way of projecting that data back outward, pixel by quantum pixel, the most profound implication. If black holes can share information through Hawking radiation and entanglement, it would mean the universe has built-in redundancy, a way to preserve its history against the voracious appetite of these cosmic shredders. Every stellar collapse, every galactic merger, every bit of cosmic history swallowed by a black hole might not vanish into darkness. It could be echoing across the cosmos, whispered between gravitational giants in a language we're just learning to hear. So while Hawking radiation might spell the eventual end for black holes, it could also be the key to their deepest connections, a reminder that in the quantum realm, nothing is ever truly lost. Just transformed, deep in the direction of the constellations Centaurus and Hydra, something massive is pulling. Not just one galaxy or two, but thousands, including our own Milky Way, all streaming toward an unseen force at 700 miles per second. Astronomers call it the Great Attractor, and it's one of the universe's most perplexing puzzles. From our vantage point, this cosmic heavyweight lies hidden behind the dense plane of our galaxy, obscured by interstellar dust and stars, making it nearly impossible to observe directly. But its gravitational signature is undeniable, warping the motion of galaxies across a mind-boggling region of space hundreds of millions of light-years wide. So what could wield such immense pull? One leading theory suggests it's not a single object, but a sprawling supercluster of galaxies, a vast metropolis of matter with gravity strong enough to bend the trajectories of entire galactic neighborhoods. Yet even this explanation feels incomplete. The observed mass of known galaxies in that region doesn't quite account for the strength of the attraction. There's something else lurking there, something invisible amplifying the gravitational tug. That's where black holes, particularly supermassive ones, enter the scene. Imagine a network of these cosmic giants, their gravitational fields intertwined like threads in a spider's web. If multiple supermassive black holes were clustered in the Great Attractor's core, entangled or linked through quantum bridges or dark matter filaments, their combined pull could explain the anomaly. Picture a team of invisible giants, each anchoring a galaxy, but their collective gravity synchronized in a way that magnifies their influence far beyond what we'd expect. It's not just the mass of the black holes themselves, it's how they're arranged, how their gravitational waves might resonate together, creating a deeper well in space-time than anyone could alone. But the intrigue doesn't stop there. The Great Attractor isn't an endpoint. It's just one piece of an even larger flow. Beyond it lies the Shapley supercluster, an even more massive congregation of galaxies pulling the Great Attractor itself. This cosmic hierarchy, galaxies drawn to the Great Attractor, which in turn is drawn to Shapley, hints at a universe woven together by gravitational currents, with black holes acting as knots in the fabric. Some theorists speculate that dark matter, that elusive substance outweighing visible matter 5-to-1, forms rivers and sheets guiding these movements, with black holes perched at the intersections like cosmic lighthouses. The most tantalizing question, whether the Great Attractor's hidden mass could include primordial black holes, ancient relics from the Big Bang that might infest the cosmos unseen. If these phantom objects exist in vast numbers, clustered in the attractor's heart, they could be the missing piece of the gravitational puzzle. Alternatively, the attractor might harbor a colossal black hole far larger than any we've observed, one that defies our current understanding of how such objects form. Either way, the Great Attractor isn't just pulling galaxies, it's pulling at the boundaries of our knowledge, daring us to look deeper. New telescopes, like the upcoming Square Kilometre Array, aim to pierce the galactic dust veil with radio waves, mapping the attractor's structure in unprecedented detail. What they find could rewrite our understanding of cosmic architecture, revealing whether black holes are silent partners in this grand gravitational dance or the unseen conductors of the universe's hidden symphony. Until then, the Great Attractor remains a reminder: the cosmos is far stranger and far more connected than we ever imagined. Capturing the first image of a black hole's shadow was like photographing a ghost. In 2019, the Event Horizon Telescope, a global network of observatories functioning as one Earth-sized lens, revealed the glowing ring around the abyss of Messier 87's supermassive black hole, 6.5 billion times heavier than our Sun. That fiery halo wasn't the black hole itself, of course, but light bent to the breaking point by its gravity, tracing the outline of its event horizon like a cosmic fingerprint. But what if these shadows aren't just static silhouettes? What if their subtle distortions, their flickers and warps, hold clues to something far stranger, a universe where black holes are nodes in a vast hidden network? Take that now iconic image of M87's shadow. At first glance, it matches Einstein's predictions, a near-perfect circle of light, warped by gravity into a halo. But look closer, the ring isn't uniform. One side burns brighter, a result of the black hole's spin dragging spacetime around it like a whirlpool, boosting light that moves with the rotation. Future observations could reveal even finer details, kinks in the ring, unexpected dimples, or asymmetries that defy classical explanations. Some theorists suggest these anomalies might hint at structures beyond the event horizon, quantum fuzz, tangled wormholes, or even imprints from other black holes entangled across the void. It's like finding scratches on a window, evidence of something pressing against the glass from the other side. The real breakthrough will come when we compare multiple black hole shadows. Imagine stitching together images of Sagittarius, a star, the Milky Way's own supermassive black hole, with those of distant quasars. If their shadows share peculiar distortions, patterns that can't be explained by their individual spins or masses, it might suggest they're not acting alone. Picture two black holes linked by a wormhole or quantum bridge. Matter falling into one could create turbulence in its shadow, while its entangled partner echoes those ripples light years away, like two drums vibrating in sync. The Event Horizon Telescope's next-generation upgrades, with even sharper resolution, could catch these whispers of connection. Then there's the mystery of black hole hair, a whimsical term for the idea that event horizons might not be perfectly smooth, as Einstein assumed, but bristling with quantum structures. If shadows flicker in ways that defy the no-hair theorem, it could mean information is escaping the black hole's grip, not trapped forever. Some models propose these quantum hairs are themselves conduits, threads tying black holes together in a web of shared data. Future shadow observations might catch them in the act, revealing not just isolated monsters, but participants in a cosmic conversation, the most tantalizing possibility. Shadows might encode the universe's hidden dimensions. String theory predicts extra-spatial dimensions beyond the three we experience. If they exist, black holes could warp them, creating subtle fingerprints in their shadows, extra ripples or spirals invisible in classical gravity. Detecting these would be like finding a secret signature in the fabric of reality, proof that black holes aren't just gravitational pits, but portals to a deeper architecture. So the next time you see that fiery ring, remember, it's not just a portrait of darkness, it's a cipher, a cosmic Rosetta Stone waiting to be decoded. And as we peer deeper into these shadows, we might not just uncover the secrets of black holes, we could glimpse the hidden threads stitching the universe together. Black holes have long been considered the ultimate cosmic dead ends, places where matter and energy vanish without a trace. But what if their infamous event horizons aren't just one-way gates into oblivion? A radical idea called the Firewall paradox suggests these boundaries might be seething with unimaginable energy, like a wall of fire waiting to incinerate anything that crosses. At first glance, this sounds like a death sentence for anything falling in. Yet dig deeper, and these firewalls might not be barriers at all. They could be the universe's most extreme gateways, hiding the keys to black hole connections we've only begun to suspect. The firewall concept emerged from a clash between two cornerstones of physics, quantum mechanics and Einstein's general relativity. Quantum theory insists that information can never be truly destroyed, while relativity paints the event horizon as an unremarkable boundary, a point of no return but not a physical wall. The paradox: if an astronaut crosses the horizon, quantum rules say they should be vaporized by energetic particles, while relativity says they'd feel nothing unusual. Firewalls resolve this by proposing an explosive quantum layer at the horizon, a literal last stand against information loss. But here's the twist: if firewalls exist, they might not just destroy, they could transform. Picture a firewall not as a destructive inferno, but as a quantum scrambler. Matter hitting this barrier wouldn't just burn, it might be shredded into fundamental bits, encoded into the fabric of space-time itself. In this view, the firewall acts like a cosmic encryption machine, translating stars, planets, or even hapless astronauts into quantum data imprinted on the event horizon. This aligns eerily with the holographic principle, which suggests black holes store information on their surfaces like celestial hard drives. Suddenly, the firewall isn't a dead end, it's a translator, converting physical matter into information that could, in theory, be transmitted elsewhere. Now imagine two black holes linked by entanglement or wormholes. If one black hole's firewall encodes incoming matter into quantum information, could its entangled partner decode it? It's a staggering thought. The very mechanism that seemed to obliterate matter might be the first step in a cosmic relay race, where information leaps between black holes like a signal across a quantum Wi-Fi network. Some models even suggest firewalls could stabilize wormholes, their intense energy propping open microscopic tunnels that might otherwise snap shut. Instead of a barrier, the firewall becomes a bridgehead, a turbulent but necessary checkpoint in a hidden cosmic highway. The implications ripple through astrophysics. If firewalls are gateways, they could explain why certain black holes seem to echo gravitational waves in ways that defy classical predictions. These echoes might be reverberations of matter hitting the firewall, its energy rippling through a connected wormhole or entangled partner. Even Hawking radiation, the faint glow emitted by black holes, could carry firewall-processed data clues not just about what fell in, but where that information might have gone. Of course, not all physicists are convinced. Critics argue firewalls violate relativity's core tenets, creating unnatural boundaries where none should exist. Others propose less violent solutions like fuzzballs, black holes with no sharp horizon at all, just a tangled quantum core extending outward. Yet even these alternatives hint at deeper structures beneath the surface, leaving room for hidden connections. Whether firewalls prove real or not, their mere possibility has already reshaped how we see black holes. They're no longer just cosmic trash compactors. They might be bustling hubs in a vast, invisible network, where the most violent processes in existence aren't endings but translations. And if we're right, decoding their fiery signals could unlock the universe's most guarded secrets. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through light years of lead without a single interaction. Born in the hearts of stars, supernova, and even black hole accretion disks, these nearly massless phantoms race across the cosmos at near light speed, untouched by magnetic fields, unfazed by matter. But what if their very stealth makes them perfect cosmic messengers? While black holes famously trap light, neutrinos slip through their event horizons like shadows through a sieve. If entangled black holes are whispering to one another across the void, these ghostly particles might be their ideal couriers, carrying signals no other medium could deliver. Consider the violent environment around a feeding black hole. As matter spirals inward, torn apart by tidal forces, it doesn't just vanish quietly. The accretion disk glows white-hot, producing not just light but a torrent of neutrinos, trillions streaming outward every second. Unlike photons, which scatter or get swallowed by the black hole's gravity, neutrinos travel unimpeded. Now imagine a second black hole, entangled or connected via wormhole, positioned light years away. If neutrinos from the first black hole's disk bear even the faintest imprint of its quantum state, a subtle fluctuation in energy or spin, their arrival at the second black hole could trigger a mirrored response. It's like two submarines communicating with sonar pulses, except here, the pulses are nearly undetectable particles threading the cosmic dark. The challenge, of course, is catching these whispers. Neutrinos are infamous for their reluctance to interact with detectors, yet scientists have already spotted high-energy neutrinos from distant active galaxies, some likely originating near supermassive black holes. IceCube, a neutrino observatory buried in Antarctic ice, has catalogued these cosmic visitors, their energy signatures hinting at violent origins, the next step. Searching for patterns repeating bursts or synchronized neutrino flares from black holes separated by vast distances. If two black holes emit neutrino streams with matching timing or energy profiles, it could suggest coordination beyond coincidence, like finding two radios tuned to the same frequency across a continent. Even wilder is the possibility that neutrinos themselves might be entangled. Quantum entanglement isn't limited to electrons or photons. In theory, any particle can share this spooky connection. If pairs of neutrinos born in a black hole's accretion disk remain linked as they fly apart, a change in one could instantly influence its partner, even if that partner has already been captured by another black hole. In this scenario, neutrinos wouldn't just be passive messengers. They'd be living threads in the quantum tapestry binding black holes together. The implications stretch beyond astrophysics. If neutrinos facilitate black hole communication, they might also carry clues about the universe's most hidden dimensions. Some theories suggest that neutrinos oscillate between flavors electron, muon, tau, because they interact with unseen extra dimensions. If black holes are somehow anchored in these higher dimensional spaces, their neutrino emissions could encode a map to realms beyond our perception. It's a long shot, but not impossible. These ghostly particles might be the universe's way of slipping us notes from its most secret corners. Of course, skepticism is warranted. Neutrinos are notoriously difficult to study, and proving they're part of a cosmic messaging system would require evidence beyond current technology. But as detectors grow more sensitive and models more refined, we might uncover anomalies, patterns that defy randomness, correlations that hint at something deeper. Whether neutrinos are mere bystanders or key players in black hole networks, one thing's certain: their ethereal nature makes them perfect spies, slipping through the universe's most guarded doors and perhaps carrying its most profound secrets. Black holes might be the universe's ultimate archivists, silently recording every event they've witnessed in a language we're just beginning to decipher. Picture a cosmic hard drive with no delete button, every star consumed, every galaxy swallowed. Every particle drawn past the event horizon leaves an imprint, scrambled into quantum code on the black hole's surface. This isn't science fiction, it's the holographic principle in action, the idea that all the information inside a black hole is perfectly preserved on its two-dimensional boundary like a celestial tattoo. But what if these imprints aren't just isolated records? If black holes are connected through entanglement, wormholes, or hidden dimensions, their combined memories could form a distributed ledger of cosmic history, a blockchain written in gravity and quantum bits. Take two entangled black holes, each storing fragments of the same event. A star collapses in one galaxy, its matter vanishing into the abyss of black hole A. Across the universe, black hole B, linked by quantum threads, might exhibit subtle changes in its Hawking radiation or gravitational wave emissions, echoing the event without ever directly interacting with it. It's as if the universe keeps backup copies of its data, ensuring no chapter of its story is ever truly lost. Some theorists even suggest these connections could create a form of cosmic redundancy, where information isn't stored in one place but distributed across a network of black holes, resilient against the ravages of time. The implications are staggering. If black holes encode the universe's history, decoding their signals could let us peer into epochs long vanished. The collision of ancient galaxies, the whispers of the first stars, even the conditions of the Big Bang itself, might be hidden in the gravitational waves and quantum fluctuations of today's black holes. Imagine a future civilization reconstructing the cosmic past not by studying light from distant stars long since redshifted into oblivion, but by reading the holographic records of black holes, their event horizons acting like rings in a celestial tree trunk, each layer preserving a different era. Yet the real mystery lies in how these memories might be accessed. If information is stored holographically, it's not as simple as plugging in a cosmic USB drive. The data is scrambled, encrypted by the black hole's immense gravity. Some models propose that only another entangled black hole could decode it, acting like a cryptographic key. Others suggest that the universe itself might provide the tools through collisions or mergers, where the violent reshuffling of event horizons temporarily unlocks the stored data, releasing bursts of structured gravitational waves or Hawking radiation that carry fragments of the past. Even wilder is the possibility that black hole memories aren't static. They might evolve, interact, or even communicate across the network. Picture two black holes that once devoured parts of the same galaxy. Their entangled states could allow their respective records to synchronize, updating in real time like mirrored cloud servers. A change in one's quantum state triggered by new matter falling in might ripple through to its partner, ensuring their histories remain intertwined. In this view, black holes aren't just passive storage devices. They are active participants in the universe's memory, constantly rewriting and sharing their chapters. The challenge, of course, is proving any of this. Unlike a book, black hole memories don't come with a table of contents. Decoding them would require breakthroughs in quantum gravity, unimaginably precise detectors, and perhaps even new physics. But the clues are already emerging. Anomalies in gravitational wave data, unexpected correlations between distant black hole emissions. These could be the first hints of a cosmic archive humming beneath the surface of reality. And if we're right, the universe's entire history might be waiting in the darkness, not lost, just written in a language we're learning to read. The next decade promises to be a golden age for black hole research, with groundbreaking telescopes and detectors poised to peel back layers of cosmic mystery like never before. Imagine LISA, the Laser Interferometer Space Antenna, a fleet of 3 spacecraft set to launch in the 2030s, floating millions of miles apart in perfect formation. Unlike Earth-bound gravitational wave detectors, LISA sensitivity will catch the faintest ripples from supermassive black holes merging at the dawn of time, frequencies too low for current instruments to hear. These waves could carry echoes of primordial connections, hints of wormholes or entangled networks woven into the fabric of the early universe. Every chirp, every tremor in space-time might be a verse in a cosmic epic we're only beginning to translate. Then there's the James Webb Space Telescope, already revolutionizing infrared astronomy. While Webb can't see black holes directly, its piercing gaze cuts through cosmic dust to study the galaxies they anchor. By mapping the motions of stars swirling around supermassive black holes with unprecedented precision, Webb could reveal subtle gravitational anomalies, telltale signs of hidden companions or distortions in spacetime that hint at deeper connections. Picture a black hole's gravity tugging on stars in ways that don't quite match predictions, as if invisible threads from distant counterparts are pulling behind the scenes. Webb might even spot quasars flaring in sync across billions of light years, their coordinated outbursts suggesting a cosmic dialogue we've yet to decipher. But the real game changer could be the next generation of Event Horizon telescopes, building on the success of the first black hole shadow image. Upgraded arrays with sharper resolution and broader frequency coverage might detect faint structures around event horizons, glowing knots or spirals that could mark the mouths of wormholes or the footprints of entangled particles. If black holes are indeed nodes in a hidden network, these features could be the signposts pointing toward the universe's underlying architecture. Some models even predict that colliding black holes could leave temporary scars in their shadows, residual warps from merged connections that linger like cosmic fingerprints. On the theoretical front, advances in quantum computing could simulate black hole dynamics at scales previously unimaginable. By modeling entangled black holes in virtual environments, scientists might uncover how information flows between them or test whether wormholes could stabilize under extreme conditions. These digital experiments could guide real-world observations, telling astronomers exactly where and how to look for evidence of cosmic threads. Meanwhile, labs here on Earth are recreating black hole conditions using ultra-cold atoms or plasma vortices, probing how event horizons might scramble or transmit information in controlled settings. The most tantalizing possibility, these tools might converge on a single revelation, that black hole connections aren't just theoretical curiosities, but fundamental features of the universe. From LISA gravitational wave symphony to Webb's galactic snapshots, each dataset could be a piece of a puzzle, revealing a cosmos far more intertwined than we ever dreamed. And if we're lucky, the next decade won't just answer old questions, it'll unveil mysteries we haven't even thought to ask yet. The universe has been whispering its secrets for billions of years. Now we're finally building the ears to listen. The universe has always whispered its secrets in ways we're only beginning to hear, not through light or sound, but through the invisible tremors of gravity and the ghostly murmurs of quantum entanglement. What started as a hunt for cosmic monsters has revealed something far more profound. Black holes aren't the end of the story, they're the beginning. Every gravitational ripple we detect, every synchronized quasar flare we observe, pulls back another layer of the cosmic curtain, showing us a reality stitched together by threads we can't yet see but are learning to trace. Take quantum entanglement, the phenomenon Einstein dismissed as spooky action at a distance. At the scale of particles, it defies logic, but when we scale it up to black holes, it becomes a cosmic lifeline. Imagine two black holes separated by billions of light years, their fates intertwined through particles that remember their shared birth. A change in one instantaneously mirrors in the other, as if the universe itself is keeping them in conversation. This isn't just physics, it's a glimpse into a deeper architecture where distance and isolation might be illusions. Then there's the symphony of gravitational waves, the vibrations of space-time itself. When LIGO first caught these ripples in 2015, we weren't just hearing black holes collide. We were eavesdropping on a language older than stars. Some theorists now suggest these waves could carry encoded data, not just about the black holes that made them, but about the hidden networks they might belong to. Like drumbeats echoing through a vast cosmic hall, these waves could be the universe's way of mapping its own connections. And let's not forget the holographic principle, the idea that black holes store information on their surfaces like cosmic thumb drives. If true, then every black hole is a library, its event horizon etched with the history of everything it's consumed. But here's the twist. If entangled black holes share quantum links, their libraries might be synced. Lose a book in one, and a copy might exist light years away, preserved in the holographic records of its partner. Suddenly, black holes aren't just archives, they are nodes in a distributed backup system for reality itself. What does this mean for us? For centuries, we've seen the cosmos as a collection of isolated objects. Stars here, galaxies there, black holes lurking in the dark. But the deeper we look, the more it resembles a living network, humming with conversations we're only starting to decode. This isn't just about rewriting textbooks. It's about redefining our place in the universe. If black holes can talk across the void, then nothing is truly alone, not even us. So the next time you stand under the night sky, remember, the darkness isn't empty. It's alive with connections, with whispers spanning time and space. And as our tools grow sharper, as telescopes peer deeper and detectors listen more closely, we're not just uncovering the universe's secrets. We're learning to read the hidden threads that bind it all together. The cosmos isn't a silent void. It's a story written in gravity and quantum echoes, and we're finally learning its language.